So we had a thing we were looking at in the previous lecture where I was talking about if you were, say, dividing by 5 and you had, say, 7/5, and suppose you wanted to use the decimal. Now, there's no problem there because 7/5 is equal to 1.4. There's no rounding error. But if, for example, you had 7/3, could you use, for example, 2.333? Now, they're not equal. They're only approximately equal. And oftentimes, using a rounded figure is no issue for you. However, with simultaneous equations, rounding is a serious issue. We'll see examples, but basically, stuff you do with matrices, stuff you do with linear systems is ill-conditioned. And what that means is if you change the problem a little bit, the solutions can change a lot. Okay, so usually a small variation like a rounding error doesn't cause an issue. So for example, we saw from last semester, if you're looking at the bending moment of a beam at the location of the maximum bending moment, if you kind of say it's whatever, if you just change that number a little bit, be it a bit of rounding error or a measurement error, only measuring to the closest centimeter, you're pretty much getting a good approximation to the correct maximum bending moment. We would have seen last semester scenarios where if you look at the bending moment away from the maximum and you've got a measurement error, that could have a big difference. I think there was one where it might have been 1 inch in the difference was something like 500 Newton meters difference in bending moment. Okay, but when things when rounding doesn't matter, that's nice. But with matrices, it's very, very different. So here you have a matrix A. So like, say, let me just explain what I'm talking about here. So if you have, say, x plus y equal to 3 and 2x minus y equal to, say, 4, you can write that as a matrix equation 1, 1. This is slightly different to what we've been doing, but it should be familiar. Okay, so it turns out, so the solutions of this are just the solutions of the simultaneous equation. So it turns out that if you just change the matrix a little bit, so this epsilon is just little differences. So instead of using 1, use, say, 0.999. Instead of using 7/3, you use 2.333. These can have very, very different solutions. Okay, so it turns out solutions of two very, very similar problems can have very, very different solutions. And it basically stems from an issue which can be kind of given like this, where if you divide by a small number, something that, for example, might be actually 0, you get serious issues. Because if the number is very, very small, you can do something. But if you do that, say divide by it, but if you do that same thing when the number is actually supposed to be 0, you get nonsense because you can't divide by 0. So we'll give an example here. We will solve this using 4 significant figures. Now this is, if to get it in augmented form, we just forget about the x and the y. Like if you multiply this out, you just get simultaneous equations. So we'll go to the augmented form. So 0.30 is a 1. And you see that's the problem because that's a small number. But if that was 0, this is a very different problem. 0.4, 0.5, minus 0.3. And then the constants are 0.5 and 0.1. So what have we learned? We should turn the thing in the top left corner into a 1, into a pivot. So we're going to do that by dividing row 1 by 0.0001. So we send row 1 to itself, divided by 0.0001. Okay, let's do that. So using the calculator, well, 0.0001 divided by itself is 1, as we wanted. And now I'll do 0.5. So 0.5 divided by that number, it'll be something like 5,000. And the constant will also be 5,000. Okay, so that's good. We've got this pivot. Now what I want to do is I want to use the pivot to turn the 0.4 here into a 0. So what I need to do now is I need to do row 2, send to itself. I want to do take away 0.4, but that isn't a row operation. So I use the new row 1 with the pivot to kill the 0.4. So it's going to be 0.4 minus 0.4 times 1. So I get 0.4 minus 0.4 times 1 is 0.4 minus 0.4 is 0. And now I'm going to use the calculator for the other bit. I'm still tired recording this. Minus 0.4 by 5,000. To 4 significant figures, so it's minus 2,000.3, but to 4 significant figures, it's just minus 2,000. And then the next one is 0.1 minus 0.4 by 5,000 as well. And that one is coming out as minus 1,999. And that's actually wrong because I put it in the calculator wrong. It's actually to the 4 significant figures, it's minus 1999.9, it's minus 2,000. So I got my 1, my pivot, and my 0. I need to turn that minus 2,000 into a 1. So what I need to do is I need to do row 2, sent to itself, divided by minus 2,000. And if I do that, the first row is grand. 1, 5,000, 5,000, and then row 2. So 0 divided by minus 2,000 is 0. Minus 2,000 divided by minus 2,000 is 1. And sorry, this minus 200 should be minus 2,000. And that divided as well gives me 1. Okay, now this is in the reduced form because you got pivot, pivot, and you got that staircase. It's in reduced form. And you know there's solutions because there's no form of the row of the form 0, 0, non-zero. So we can say that y is equal to 1. And if I do x plus 5, now look at row 1, x plus 1x plus 5,000, y is equal to 5,000. And if y is equal to 1, we get x plus 5,000 is equal to 5,000, which means that x is equal to 0. So our solution of this, using 4 significant figures, is that x is 0 and y is 1. So we find answer, you can write it like this maybe, x, y, x is 0, y is 1. Okay, now you're going to be in for a small shock now because that is miles off. It turns out the correct solution isn't 0 and 1, but both of them are close to 1. So the issue is the rounding. It causes a mayhem here. So basically the issue, if I can, it's dividing by this 0.0001. So what that does is it amplifies this 5,000 and this one. So these both get rounded because they're both really, really big. But actually they shouldn't, well, they should be the same. Okay, sorry, what happens is, you see these two numbers are different, but because you divide by such a small number, you get up these massive numbers, 5,000, and they completely swamp the little minus 0.3 and the 0.1. So these really shouldn't actually be equal, which means that y shouldn't be exactly 1. And if y isn't exactly 1, you won't get that x is 0. So the issue is dividing by a small number. So there's a big spiel here that I don't really want to go through, but I'm just gonna you can read it if you want to kind of understand what's going on. You avoid small pivots. So when you see this, when you're rounding, this should be sending off alarm bells. So what you do to not have the problems that we saw is that you swap the two rows. And if you swap the two rows, what happens is you won't be dividing by a very, very small number. You won't see the same problems. Okay. Now, is this guaranteed to work? This, by the way, swapping the rows, and we will see examples, is called partial pivoting. It's not guaranteed to work, but basically it works whenever you need to. Okay, so on a computer that might be solving simultaneous equations using these methods, computers can't store like thirds properly, most of them. So they'll store like 0.33 with 16 trees. They'll have to do the partial pivoting or else they're getting really bad errors. Okay, so when we are rounding, we have to do partial pivoting. Now, usually what will happen in a question is I'll say, pretend you have to round, and then you do partial pivoting. If you're just doing a question otherwise, and there's no mention of rounding, don't round, use fractions. Because if you round, your answers can be miles off. If you insist on rounding, I'm not going to be happy. But if you insist on rounding, you have to do partial pivoting. Okay, right. So the beauty of this Gaussian elimination is when you have the augmented matrix or the coefficient matrix brought into the row echelon form, you can tell if solutions exist. We actually looked at this in the previous lecture. So if you get a row that is like loads of zeros and something non-zero, then there's no solutions. Now, if this 2 is 0, there's no problem. But look at what this row corresponds to. If it's, say, x1, x2, x3, this says that 0x1 plus 0x2 plus 0x3 must equal 2. But of course, 0x1 is 0, 0x2 is 0, 0x3 is 0. Add those zeros together, you get 0 is equal to 2. And what this is absolute nonsense. And what happens here is that when you write down the equations, like with the truss, you assume that the structure is stable. When you write down equations, you assume that there is a solution. So if you assume there's a solution and you get nonsense, the original assumption of solutions is wrong. There is no solution. Now, that logic might be a bit tricky for us. So basically, whenever you see a row like this, 0, 0, 0, non-zero, there's no solutions and you're done. If no such row appears, then there is at least one solution. So that's what I was talking about last day. I asked, is there not no solutions? It's unique if every column contains a pivot. And if this is not the case, then variables, columns without pivots are what are called parameters. So they are values that can take on, they're variables, they can take on any value at all. Now that might seem a bit weird, but I think when especially we get into context, that will start to make a lot more sense to you. Okay, so here we got 3 examples. So first of all, let us note that we've got our pivots. And let us also note that we're in the reduced form because you've got this staircase going on. Now you can't do the analysis we're about to do until you're in this staircase form. Okay, so the first one, what you have to say here is that there are solutions because there's no not solutions. So simply at the start there are solutions because there's no problem row of 0, 0, 0, non-zero. And then you read from the bottom, it's quite easy. So the last row, if it's say x, y, z, it will say x1, x2, x3. It's 1, x3 is equal to 2. That's what the bottom row says. The second row says 0x1 plus 1x2 plus 0x3 is equal to 0. In other words, 1x2, which is x2, is equal to 0. And similar story, the first row says 1x1 is equal to minus 1. Now, if you want, you can try and get all these more zeros knocking around, but you don't have to, right? What I'm saying is maybe you want to say, oh, I want to say, oh, these zeros are nice, aren't they? But you can't always do it. Don't worry about that too much. That's what I'm saying. Okay, so that's that has, okay, what's the big ticket here? The big ticket for question 2 is it's a unique solution. I might say, oh God, you might say there there are 3 different solutions. No, there's only one solution. It's for x1 is this, x2 is this, x3 is this. Now look at the third row in this one. 0x1 plus 0x2 plus 0x3 plus 0x4 cannot equal to 2. So this one has no solutions. That's great. There's just no solutions. Now this, yeah, okay. Now the third one, there are solutions. The final row is no issue at all because it just says 0 is equal to 0. That's not a problem. 0 is equal to 2 is a problem. But what you have is, so there are solutions. So there are solutions. I might just write that in a second. But what I want you to note is the pivotless columns. So x2 has no pivot in it, and x5 has no pivot in it. We might just point out and say that there are solutions to the third one. Okay. So it turns out that the theory says that you can always take, if there are solutions, variables corresponding to pivotless columns to be parameters. They can take on any possible value. Now you could just leave them as x2 and x5 and just say the parameters, but I think it's nice to give them different names to kind of emphasize this. So usually what I'll do is we'll call the last one, or the last one in this sense, t. And if you have another one, you can call it s. I don't think I give you a problem where there's more than 2 parameters. Okay, so what is x5? x5, I'm telling you, can be anything. So for every possible value of x5, there is a solution, is what that says. Infinitely many solutions, therefore. So look at the second last row of this third one. So it says 1x4 plus 2x5 is equal to 6. So it says 1x4 plus 2x5 is equal to 6. We know that x5 can be anything. We're calling it t. And now what we find is once we know x5, if we say if x5 is equal to 3, we're going to be able to find x4 in terms of it. So take away the 2t from both sides here. You get x4 is equal to 6 minus 2t. Okay. Now we look at the third last row. So it says x3 plus 4x5 is minus 5. x3 plus 4x5. Yeah, one of the things is if you have the manual printed out, it's easier because this scrolling is easy if it's printed out in front of you, equal to minus 5. Now again, we know that x5 is equal to t. So you got x3 plus 4t is equal to minus 5. And you can take away the 4t from both sides. x3 is equal to minus 5 minus 4t. And now, so yeah, and then we have finally looking at the very first row, it says 1x1 plus 5x2 minus 2. Yeah, I'm going to start right here. So it says 1x1 plus 5x2 minus 2x5 is equal to 3. I know that x2 I'm calling s as a parameter, x5 I know as a parameter I'm calling t. So I end up with x1 plus x2 is s minus 2x5 2t is equal to 3. And I need to take away the 5s from both sides, add the 2t. So I get that x1 is equal to 3 minus 5s plus 2t. Now what we can say here is that you will understand a bit better the parameters when we do go into context. So at the moment it might be a little bit difficult, but maybe after lectures next week it'll make a bit more sense. So we get our solutions like this. So x5 is t, x4 is 6 minus 2t, x3 is minus 5 minus 4t, x2 is a parameter s, and x1 is 3 plus 2t minus 5s. And there's a doubly infinitely many solutions. Okay. Why did we need two parameters? So basically I'm going to write down the theorem. It's and this is connected with the analysis of truss. So suppose the augmented matrix has R pivots. Now essentially the number of pivots is essentially the number of equations. You might start with more than one, say 3 equations. You might have 4, but some of them, it might be actually not independent of the other ones. So it looks like you got, so I'll show you what I mean. So suppose you got x plus y equals to 5 and 2x plus 2y equal to 10. You don't actually have 2 equations because those equations are the same thing, because you can multiply the first one both sides by 2 to get the second. So when you do the row echelon, when you do the Gaussian elimination, the row stuff, it'll get rid of these kind of relationships between different rows. And when you get there, the number of equations you have will be the same as the number of pivots. Okay, if there are solutions, so you have to check are there solutions first, then the gap between the number of variables, which is n, and the number of equations is the number of parameters. So that kind of goes back to the truss system, the truss systems. When there are loads of variables but not enough equations, you do not have enough information to find out the values of all the forces and stuff. And so you have a situation where there's infinitely many solutions if there are solutions. Yeah, so if you have a parameter, you have infinitely many solutions. Each pivotless column can be assigned to a parameter. If there is exactly the number of equations as variables and there are solutions, there's a unique solution. And that's about the determinate truss. Okay. So it seems so that there are 3 possibilities. There's no solution, and that is when you have 0, 0, 0, something non-zero. There's exactly one solution. So what this means is no parameters. Every column has a pivot. Yeah. And then infinitely many, this one's you have at least one parameter. And because the parameter can take different values, infinitely many values, each value of the parameter gives you a different solution. So essentially, or this is what we said, or represents number of independent equations. Yeah, so we said that. So this is the Gaussian elimination algorithm. So basically, we won't follow it like that. We'll just go for a pattern that we want. So that's all the theory. In the final lecture of this week, we will do 3 examples.